Let's wait for a couple of minutes. Let's see if other people also join. Just 1 or 2 minutes. Okay, so let's start. In the last week, okay, so this is week 5 of the session of the TA sessions on this course on design and analysis of algorithms. And due to medical reasons, I had to prepone my sessions for the next 2 weeks. There will be a session tomorrow at the regular timings, 3 to 5. But then next Saturday, there won't be any session. So in the previous session, we started our discussion on searching on basically the graph problems. And one of the most common problem in graphs is to traverse the entire graph or to search for a node in the graph, right? So let's say we want to, we are not interested in a particular node, but we want to search the, we want to traverse every node in the graph once, right? So there are two ways to do so. One is BFS, right? Wherein when you start at a node, then you, in the next iteration, you are going to traverse all the nodes which are adjacent to this node and have not been visited before. And that continues. Then there is DFS, the depth first search, wherein when you start exploring a node, then you go to an adjacent node which has not yet been explored. And so every time you start exploring a node, if there are nodes which are adjacent to it and have not been explored yet, you will suspend the exploration of the current node and move on to the adjacent node. So from a node, once all its adjacent nodes have been fully explored, we will finish the exploration of the current node. So that is the idea behind depth first search. The main, these numbers that we assign for every node when we start exploring a node, and the time when we are finished with the node, which we call as the start and the finish numbers, these are particularly useful in solving some of the uh, nice problems in graphs, related to graphs. So we will see two applications of DFS. The first one will be about the strongly connected components. But before that, let's see a few questions on related to these numbers, so that our understanding, we have a very good understanding of these start and finish numbers, and these different edges that the various classification of the edges when we do a DFS, including the tree edge or the back, forward, cross edge, how they are related for these edges, how do the start and finish numbers are related, right? So when we do a DFS on a, okay, let's say we do a DFS on a directed graph, and we can have different types of edges, right? One is we can have tree edges, which are basically used to traverse the entire graph, go from one node to the other node. Then we can have non-tree edges. The other is non-tree edges. And in these non-tree edges, we can have a back edge, a forward edge, or we can have a cross edge. Okay, so all these edges are non-tree edges, right? So every edge in the directed graph that we have can be classified as either a tree edge or a non-tree edge. If it's a non-tree edge, it can be either of the back edge, forward edge, or cross edge. Let me let's see in general how does a DFS tree looks like. So let's say that's the root node, and it can have several, we can have several paths starting from the root node. Even within that, there can be several branches and so on. Okay. So what we had discussed is that with every node in this DFS tree, there is an interval associated to the starting number, and the finishing number associated with that node will essentially give you an interval. Okay, so the first thing we had observed was that these intervals have along a path has a nesting property. So the largest interval would correspond to the tree node with the root node. And then if you look at, let's take this first path, right, the one to the left. And if you look at the intervals corresponding to the nodes on this path, it's going to be to follow a containment. So this, something like this. So intervals get smaller, and they are all contained in the original interval. Okay, so essentially you have this containment relation as we go down the down a longer path in the tree. And if I look at two, let's say I have this another path, right? This path, sorry, this path over here, which branches out somewhere in the middle. Again, the will have intervals corresponding to every node in that path. And again, they will follow the containment relationship. It's difficult to draw it like that. Yeah, let me draw very few intervals so that at least the figure doesn't look wrong in any ways. So what we have is, if you look at a DFS tree for a given graph, if you follow a particular path in that DFS tree, these intervals will have the containment relationship. Okay, so there is, let's say I have two nodes along this path, let's say U and V. Then what we see is that the interval for V will completely lie within the interval for U. So the starting time for U is smaller than the starting time for V, and the finishing time of V will be smaller than the finishing time of U. The second thing is, if I take any two paths in the tree, two different paths in the tree, and I have, let's say, a node in one path and another node in the other path, then their intervals cannot, they will be completely disjoint, right? So we'll have along one path, you will see the containment relationship. So these intervals keep getting smaller, and it's always follows this containment relationship. And if I look at two nodes along uh, on two different paths in the tree, their intervals will be completely disjoint. Okay, so now in case of a tree edge or a forward edge, right? So how does a tree edge looks like? Let's say I have this. So let's say I have this tree edge over here. So let's say node U and V, it's a tree edge. So what we have is that the interval for V is completely contained within the interval for U. Similarly, if I have a forward edge, let's say I have a forward edge. So how does a forward edge looks like? In case, suppose I take any path on the tree, and so if I take two nodes on a path in the tree, then they will have the ancestor-descendant relationship, right? So from one of the ancestor nodes to a descendant node, you will have an edge. So this is not a tree edge, it's a non-tree edge. So this is a forward edge. I'll in short write as F, right? So that was a tree edge, T for tree. I can help you understand, like I can, in the previous week, I actually did BFS and DFS surveys. So BFS, maybe even if it is not clear, it's fine because I'm not going to use this for today's class. But it's important to have a good understanding of DFS. I'm actually trying to explain the DFS all over again. But if you want, I can go from scratch. So I can give a quick review of DFS. Uh, Most important things are these start and finish numbers. Once we have a good understanding of that, we'll be able to understand the problem that I'm going to explain today. So do you want me to do that?
Okay, ma'am, no problem. Uh, Hello.
I'm not able to hear you. Did you say something? Okay. Yeah, but it would be nice if you can unmute yourself and that way it will be more interactive and help me also in being able to see what. Okay, okay, no issues. Then we can talk through chat. But yeah, then be responsive on the chat. Okay. Yeah, you can maybe try to rejoin once and then see if the mic works.
Oh, ma'am, am I audible now?
If you are trying to say something, I'm still not able to hear you, but
Hello,
it's okay if
ma'am.
we can, you can write your queries in the chat and I can answer it over there.
Okay, ma'am.
Okay, so in DFS, uh, let's say I have a directed graph. We can apply DFS on an undirected graph as well. But this is like this involves when you do a DFS on a directed graph, you get the edges classify into four classes actually. So let's say I'm given this directed graph, right? And I can pick any of the node to start with that will form the root of my tree in the while doing the DFS search. So let's say I start with the node J. Okay. So what I'm going to do is whenever I start exploring a node, to that node, I'm going to assign a start number. And once I'm done finishing with that node, I'm going to assign something called as a finish number, right? So that is all we have to do. So, and the procedure is as follows. I start with J, I assign it a number 0. Then I look at the outgoing edges from J and pick one of the two nodes, right? So let's say whenever we have a choice, we pick the nodes in dictionary order. So between G and L, I'll pick G. So when do I start exploring G? I start it at time 1. So every time my counter is going to increase by 1. I will keep track of a global counter. Initially it was 0. That is the time when I started exploring J. At time 1, I start exploring G. Then from G, I see what all outgoing edges we have. There is one outgoing edge to I. So I'll start exploring I at that point at time 2, right? So at 0, we started exploring J. At time 1, we started exploring G. At time 2, I'll start exploring I. And once I'm done, here I see again the outgoing edges, but it goes to a node which has already been visited, right? So I cannot explore any other node from I, right? So I'll be done with I at time 3. Then I come back and go back to its parent meaning from where I had actually started exploring I. So I go back to G. Then from GIC, is there any other outgoing edge? Going to a node which has not been visited yet. There is none. So at time 4, I'm finished with G. Go back to its parent. I come back to J. From J, I again see is there any other outgoing edge to an unexplored node, and we see yes, there is a node. So at time 5, I'll start exploring L. Okay, so from L I go to K at time 6. From K, I go to H at time 7. From H, I see there are two outgoing edges, but both of them have already been visited, right? So I get finished with H at time 8, go back to its parent. There is no other node to explore from K. We get done with it at time 9. Come back to L, which is the parent of K. From L, there are no other outgoing edges. So we get done with it at time 10. And finally, come back to J. From J, again, I see that all the adjacent nodes have been fully explored. So I assign it a finishing time of 11. So that is how the DFS proceeds, right? I've just redrawn it as a tree over here. Okay. So these orange edges that I have marked, these are the tree edges, which I use to traverse the entire graph. Okay, so here I'm showing them as black edges. And if I look at the non-tree edges, which I did not use to explore the graph, these edges can fall into one of these three classes. Either it will be a forward edge. By forward edge, I mean, it will be a back edge. By back edge, what I mean is, so let's say I consider this path in the tree, DFS tree. Okay. So when I come to I see that there is an edge going back to J, which has already been visited. Okay. So this is what I call as a back edge. So it connects a node to its ancestor in the tree. It could be parents also. I mean, a back edge can also connect it to its parent. Means we will consider the parent also as an ancestor. So that is the back edge. Okay. Forward edges, when you have something like this. So it goes from a node to one of its ancestor, not the child. So any edge connecting a node to its child, that is the tree edge. A forward edge will connect it to a ancestor. Right? It's just the reverse of the back edge. And finally, we can have edges which connect two nodes in two different paths in the tree. So in that case, there is not, we will not have any ancestor-descendant relationship. It's just that there is an edge going from a node to another node in some separate path in the tree. Such an edge is called a cross edge. So if you look at a back edge, then you see something interesting happening. The intervals corresponding to the two nodes will have the containment relationship, right? So for instance, here I have a back edge from I to J. The interval 0 to 11 corresponding to J contains the interval 2 to 3. So we'll have this containment relationship. The same holds for tree edge and forward edge. If you look at this tree edge, so 0, 11 contains the interval 1, 4. Similarly, if I look at this forward edge, so this was not there in the example we took. I just wanted to show what we mean by a forward edge. So here also you see this containment relationship. Right? 0, 11 contains the interval 6 to 9. And finally, if I consider cross edges, we can see that they are going to be completely disjoint. 1, 4 and 7, 8. These are completely disjoint intervals. So is that clear? Okay. So now based on these understanding, now let's look at a few questions. Um, the first thing is, as we had discussed so far, that along a path in the tree, there will be containment relationship, right? The intervals will be contained. This will be the longest interval, then it will contain a shorter interval. This will contain a even shorter interval, and so on and so forth. And if we take two nodes along different paths in the tree, then their intervals will be completely disjoint. So one question is it possible to have two intervals which partially overlap? Right? So can we have two nodes in the DFS tree whose intervals partially overlap? Can we have such a scenario? Uh, can we have such a graph such that if I do a DFS on that graph, then let's say I get some DFS tree. Is it possible that two nodes in the DFS tree have their intervals partially overlapping, meaning something like this? Let's say that's the interval corresponding to, why did I get? Let's say that's the interval corresponding to a node U. And then there is another node V, and its interval starts somewhere in the middle of this interval and then finishes later on. Can we have such a situation? How can we have?
मैम लेके हेलो
Let's say I have, that's a root node in my DFS tree, and consider some path in this tree. Okay. And I have a node U in this tree. Right? Actually, this is not possible. So I'll explain why is it not possible. So let's say I have this node U in the tree. I started at some point, some time, right? And start exploring it. And then uh, at some point, I see that I need to, let's say you had the adjacent neighbor V, and V is not yet explored. So from U, I'm going to actually start exploring V, right? I'll go and start exploring V next. Now, when I start exploring V, its interval, its start time will be more than the start time of U, right? It will be larger than U. So as a concrete example, let's say I start exploring U at time 4, then I come to V and start exploring it at time 5. So V was an immediate neighbor of U, let's say. Okay. So V's start time has to be larger than the start time of U. Now, how is it possible that when I assign the finishing time for U and V, V's finishing time is larger than the finishing time of U? So once I have come to V, I will, suspend exploring U. I will start exploring V now. And until I finish exploring V, I cannot go back to U. So I have to first finish V and then go back to U. So from here, I'm going to start, you know, exploring the adjacent nodes of V. And from there again, might have to explore other nodes. So essentially, I'm going to get a subtree here. And once I'm done with this subtree, once I have assigned the start and finish time to all the nodes in this subtree, then I'll come back to V and assign it a finish time. So let's say I assign this a finish time of 10. Once I am done with V, then I go back to U and see if there is some other tree that some other node that I need to explore from U. Some other node that is adjacent to U and has not been explored yet. So if there is one, in that case, I'm still not going to assign any finishing time to U. Okay? If there are no other nodes, then I'll assign it a finishing time of 11. But if the other possibility is that there still are nodes which are adjacent to you, have not been explored yet. In that case, I'm going to fully explore that node and then some subtree of that node. We need to complete this exploration and finally come back to finally come back to U. And let's say exploring this entire region takes some time. There were few nodes here, and I'll finally assign it a finishing time, let's say 20. So such a situation will never arise where you have just a partial overlap. That is not possible. If I start a node U and I haven't assigned it a finishing time, then and I somehow suspend this exploring this node, I start exploring this other node, I must finish this node before I finish U. Okay, so the finishing time of V has to be smaller than the finishing time of U. So there are only two possibilities. Either one interval contains the other interval, which is true in case of a tree edge, a back edge, and a forward edge, or the other possibility is that the two intervals do not overlap at all. They are completely disjoint, which is the case of a cross edge. Okay. So this is not possible. Okay. Yeah. So we should finish before U. Now, this is when we do DFS on a directed graph, we get, these different types of edges besides the tree edge. What happens if we do a DFS on an undirected graph? Then what all edges can we get? Yeah, please try to rejoin. Yeah, I think it would be better if the mic works. So is the other student Sagar? Oh, is Sagar, did you try saying something? Is it, can you check if your mic is working? Because other student was also.
Hello. Is it working?
Maybe I am not able to. Is I think the problem is with my speaker in that case. I cannot hear anyone. Yeah, I'm not able to hear. The problem might be with my speaker. I don't know how to fix it.
Ma'am, am I audible now?
Sarvesh, maybe the problem is from my side. My speaker might not be working because the other student is also trying to say, and I'm not able to hear them. Um,
Okay, ma'am.
I'm really, yeah, it's not because if I end the call and then let, so I will not end the meeting. Let me leave the meeting and rejoin if that can work, because what I think is I'll need to switch off my system and then restart it. But then that would end this meeting and restart another, and we have to upload one single meeting for a TA session. Anyways, let me just try leaving and rejoin once. If let's see if that works.
Ma'am, am I audible now?
Hello, ma'am.
So one of you can unmute and I just wanted
Hello.
to see if my
No, ma'am. I think not working.
okay, so there is problem with my system, my side. I'm sorry, but today we'll have to just interact via chat only. Yeah, tomorrow there will be a session, 3 to 5, but next Saturday there won't be any session. I'm really sorry for today. I I don't know what's wrong with my laptop. Okay, okay. Yeah, so let's say if I had an undirected graph, right? In that case, yeah, in that case, when we do DFS, what all types of edges we can get, right? I'll just take a very simple example, right? Let's say I have just 3 nodes. And it's an undirected graph. Let's say the nodes are labeled as A, B, and C, and I want to do a DFS on this. Okay, so this is node A, B, and C. It's a complete graph, a triangle graph. And let's say we start with A, right? You can start with any node here. All are symmetric in the sense that every node has degree 2. It's a complete graph. So let's say I start with A. So I will first, visit A. And at what time I'm visiting this? I'm visiting this at time 0. Okay. Then I'll go and see if there are neighbors of A which are not yet explored. So there are two neighbors, B and C. And as I told you, whenever there is a choice, I'm going to pick the node which comes first in the dictionary order. Right, so I'm going to pick B next. Okay. So I'll use this edge to visit B. So this edge, whenever we are using an edge to visit another node, that's going to be a tree edge. Okay. So I'll visit B and I'm visiting it at time 1. Right? So that's a start number for B. Now from B, I see if there is any other node that I need to visit. So there are, B has two neighbors, A and C. A is already visited, so we'll not revisit it. We'll visit every node exactly once. C is not yet visited, so I will use this link or edge to visit C. So this is my other tree edge in the DFS tree. I'll visit C at time 2. Now, once I'm so at C, I see that there are no more other nodes that we can visit. C has two neighbors, but both of them have already been visited. So we are done with C. Nice. We are done with C at time 3. Okay. I go back to its parent, which is B. And from B also, there are no other nodes to explore. So I'm done with B at time 4. Finally, from B, I go back to its parent. From A again, I cannot explore any other nodes. So we are done with A at time 5. Okay, so that is how the DFS is done. And we assign the start and finish numbers. Okay. So these orange nodes that I had, orange edges that I have, these are the tree edges. So can one quickly tell me that this third edge, what is the type of this edge? Back edge? Sarvesh, is it a back edge or a forward edge? This edge. So here is the tree, right? I started from A, I go from A, I went to B, from B, I went to C, and from C, there is one edge which connects to A. These two edges are tree edges. What is this edge? Yeah, right. So it actually it's you can call it a back edge or a forward edge. I mean, it's the same thing. The only difference is because it's an undirected graph, the back edge and the forward edge actually have, they are one and the same. Right? So if I have a forward, in case of a directed graph, if I have a forward edge like that, if I change the direction, it will become a back edge. So since in an undirected graph, edges do not have any directions, it's one and the same thing. And we refer to them as back edges. We don't call them as forward edges, we call them as back edges. And now the question is, when you do a DFS on an undirected graph, can you get some, we have seen, okay, there will be tree edges. This back and forward edge are one and the same. We'll refer to them as back edges. The question is, can there be a cross edge in an undirected graph? Is that possible? in an undirected graph, when we do the DFS, can we get a cross edge as well? So cross edge meaning, let's say I have two different paths in the DFS tree. Pick two nodes in those two paths. Okay, let's say I have a node here on this path and some node on the other path. Okay, so any edge going from which connect two nodes which are on different path, meaning that they don't have a ancestor descendant relationship, that kind of edge is a cross edge. So let's say I had some vertex on in AB and some other vertex along, let's say there were multiple, there are multiple nodes here. So what you are trying to say is, if there is a node here and a node here, then any edge connecting them will be a cross edge. No, right? This is not a cross edge because two nodes here, they have the ancestor descendant relationship. Okay, so cross edge is not possible. Let's say I visit a node, and I see that from this node there was this edge in my graph. Okay, now if it is a directed graph, maybe this edge was pointing towards this node. Then I cannot, let's say this is A, this is B. Then I cannot visit B from A. Okay, so what will happen is later when I visit B, I'll see that, oh, there is an edge going to A, but A is not an ancestor of B. That is why we are calling this as a cross edge. Okay, it's connecting two nodes along different paths in the tree. Now consider the scenario where this edge did not have a direction. Then when I'm exploring A, I'll see that it has a neighbor B which is not yet explored. So I will explore B from A only. So B will become a child of A in that case. So there will be no cross edges in doing DFS on an undirected graph. We will either have every edge will be a tree edge or a back edge. That is it. Yeah. Now, dear, because I think it's difficult for you also to keep typing, what I'll do is I'll take a break here. Maybe I'll just end the meeting. I'll end the meeting. I'll not end it for all, so you can stay connected. My iPad is connected. I'll turn off my laptop and then restart it to see if that fixes the speaker issue for me. Okay, so it will take time. Maybe we'll take a 10 minutes break. In case that doesn't like the speaker doesn't work, then I cannot do anything. Maybe later I'll try. But for now, let me just end it and restart my system. Okay, we'll resume it in 10 minutes. I request you to stay connected. Okay.
Hello, hello. Mm,
Is my screen visible? Oh, am I not audible now? Hello? Hello.
Hello?
Am I audible now?
Yes, ma'am. Hello? Ma'am, am I audible?
Am I audible? Okay. I also wanted to test my speaker. Yeah, I could not. So I think the speaker has gone bad. There might be issue, hardware issue. Actually, I dropped my laptop just a few minutes ago. Maybe because of that, it is not working. Okay, so screen is visible and I am audible, right? Okay.
Hello, ma'am.
So, one quick question here. From now on, let's focus on the directed graphs only. Right? We'll see a nice application using DFS on directed graphs. Now, can you quickly tell me which of these four edges lead to a higher finishing time? So for instance, what I mean by that is, let's say I have a tree edge from U to V. Okay, I have this tree edge. In that case, I know that this edge leads to this. I mean, the finishing time of V is smaller than the finishing time of U. That means the tree edge does not lead to a node which has a larger finish time. It will lead to a node which has a smaller finish time. Same is the case with forward edge, right? So if this node had a finishing time somewhere here, this will finish before that. So again, forward edge is also leading to a node with a lower finishing time. So we are now left with back edge and cross edge. So which of these two edges will lead to a node with a higher finish time? Back edge, Sarvesh? No. So cross edge is, so, let's say this is a cross edge, right? So it's going to a node which is already finished. So again, this is also leading to a node with a lower finish time. Okay, so it's only back edge. So I forgot to draw it here. Let's say I had, so this was a back edge. only a back edge is going to take you to a node with a higher finishing time. Because as we move from, as we uh, move down a path, okay, move along a path from top to bottom, the finishing time will keep on decreasing. Okay, so if it either it's a forward edge or a tree edge, those are going to take me to a node with a lower finish time. You see, the finishing time keeps on decreasing. Starting time will keep on increasing. But it's only the back edge that is going to take me to a node with a higher finishing time. Okay? In case of cross edge, it goes from, it connects two nodes which are on different paths. Plus, I'm going to go to a node which has already been finished. Okay, so its a starting time is going to be larger than the finishing time, and therefore the finishing time will also be larger. So the finish time is of of so if there is a cross edge from U to V, V has a smaller finishing time. So here is the key property: only the back edge leads to a node with higher finish time. Now, have you gone through the topological sorting that's covered in the course? Okay, so first of all, for topological sorting, we need to have a directed acyclic graph, right? DAG in short. So DAG means it's a directed graph, but it does not have a cycle. Directed acyclic graph. Now, what do we do in topological sorting? Also, you should, from the discussions that we have had so far, should be immediately clear that if I have a cyclic graph, either directed or undirected, it is equivalent to saying that there is at least one back edge. So only the presence of back edge guarantees that the graph is cyclic. It can be either a directed graph or an undirected graph. So if it's a directed graph, the forward edge will not, just having the forward edge and cross edge, they will not create cycle. Only the back edge will create a cycle. Okay? And that's true in undirected graph as well. Now, let's say I have a directed acyclic graph. It means that if I do DFS on such a graph, I'm not going to get any back edge. All the edges will be either tree edge or forward edge or cross edges. Okay. Now, what do we mean by topological sorting? So topological sorting is essentially I want to sort the vertices, order the vertices of the graph so that in a linear order, So let's say the vertices are V1 to Vn. I want to sort them. Let's say that is V1, V2, and so on up to Vn. So in such a way that if there is an edge from, let's say, Vi to Vj, let's say I have an edge from some node Vi to Vj, then it must be pointing in the forward direction. Okay, so I need an ordering on the vertices of the graph so that if I take any edge in the graph, in the original graph, it must be pointing in the forward direction. That is what we mean by topological sorting. Okay, so in the course, I think Professor Madhavan did it using an algorithm that is based on something called as identifying the source vertices. Right, you identify a source vertex in the graph. Right? So every directed acyclic graph will have a source vertex and a sink vertex that you can easily prove. So source vertex meaning it will have only outgoing edges, no incoming edges, right? So its in degree will be 0, and a sink vertex would mean that it only has incoming edges, no outgoing edges. So out degree will be 0 for a sink vertex. So one way to get the topological sorting is you identify a source vertex, take that as your first vertex, right? So this is a source vertex. So I know that all the edges from this vertex are going to be in the forward direction, and then you recurse, right? So what I mean by recursion is delete this vertex from the graph, from the original graph, and because it was acyclic to begin with, the graph was acyclic. Even after deleting a node and edges associated with that node, the graph will be acyclic. So I should be able to find a source vertex in the remaining graph. So list that down as a second vertex and continue. That way, the ordering that you get will be topological ordering or topological sorting of the vertices of the graph. Now, we can also do this topological sorting using DFS. So can you think of how do we do topological sorting using DFS? Let's say I have run my depth first search on the graph I was given. Now, based on this starting and the finishing numbers, right? Every node will have a start time and a finish time. So essentially based on finish time, I want to find a topological ordering of the graph. How do we do that? Okay. What about Sagar? Can you answer this? Can we do topological sorting using DFS? Yes. How? Yeah. What order? So decreasing or increasing order? So you first run the DFS on the graph, right? So you are given a graph. You're first going to run DFS on that. So for every node, you're going to maintain the start and finish time. Now, once I have this finishing time for every node in the graph, then I will just write the vertices in the decreasing order of finish time, and that should work, right? So the algorithm is as follows. You run DFS. And order the vertices in decreasing order of finish time. And why this should work? Because why this will work is, let's say I take two vertices in my graph, U and V, and I know that the finishing time of U, let me denote that as F of U, is greater than the finishing time of V. So what can, so suppose there was an edge from U to V. What will be the direction of that edge? Will it be from U to V or V to U? Try to answer this based on this observation. Only the back edge leads to a node with higher finish time. And when you do a DFS on a DAG, because it is acyclic, there won't be any back edges. Sarvesh? Yeah, exactly. From U to V. Okay, good. Right? So all the, when you order them in the decreasing order of finishing time, if I pick any two vertices in that ordering, I know that any edge between U and V must be in the forward direction because it has to go to a vertex with the lower finish time. Okay, because it's only a back edge that will lead to a vertex with higher finish time, and in case of a acyclic graph, I cannot have a back edge. So see how simple this topological, how simply we can do topological sorting using DFS. Just run the DFS on the graph. Every vertex will have a finish time, and then you order the vertices in the decreasing order of finish time. Okay. Now that we have a understanding of these, start and finish numbers, the topological sorting also. Now we can now move on to a nice application of depth first search. This is also one simple application of DFS. Uh, if I want to do a topological sorting of an directed acyclic graph, I can use DFS to do it. And let's look at some more non-trivial applications of DFS. So one is, I think I did not discuss this problem in the previous session. Yeah. So the problem is finding something called as the strongly connected components of a graph. Of a directed graph. Okay, so if it's an undirected graph, we just call them as components. So we'll see strongly connected components in directed graph. So identifying components in an undirected graph, that is easy. You can think about it, how to do it using BFS or DFS. But in case of a directed graph, finding these strongly connected components using DFS. This uses some very nice observations. So we'll discuss those one by one, and then we will see the entire algorithm of finding these strongly connected components. So let me first explain what SCCs are. I'll copy this figure. So let me extend this graph. And one thing to note is that even this graph that I have, right? So when we did a DFS on this graph, starting from J, I was able to reach every vertex in this graph. Okay. Now, what I mean by a graph being strongly connected. So before going to the strongly connected component, what we mean by a strongly connected graph is if I take any two vertices in that graph, any two vertices, let's say U and V, I must be able to find a path from U to V and a path from V to U. So every pair of vertices, if every pair of vertices in the graph are connected by paths in either direction, then we say that the graph is strongly connected. Okay. Is this graph strongly connected? See, when I do this DFS starting from J, I was able to get one DFS tree, right? So what it means is from the node J, I have a path to every other vertex in the graph. Okay, so let's say, so I have like 6 vertices in the graph. I can have 6 different ways of doing a DFS. Like it depends on which vertex I start with. Let's say I start with J first. I see that, okay, I get just one DFS tree. That means there is a path from J to every other vertex in the graph. And then I can run my DFS starting from I. Okay. So when I start from I, again, if I see that there is one single DFS tree I'm getting, in that case, it means that from I also there is a path to every other vertex, right? So I will do that with every vertex as the start vertex. And if for every vertex I get one single DFS tree, it means that the graph is strongly connected. That is one way of checking whether a graph is strongly connected or not. Okay. So in this case, yeah, this is a strongly connected graph because here it is, we can see that there is this cycle. Okay. In fact, there is this cycle. This cycle makes it easy to observe that this graph is strongly connected, because once we have a cycle, I can go from any node to any other node in the graph. Okay. So this is a strongly connected graph. So we also have what is called as a weakly connected graph. Weakly connected means there will be at least one pair UV such that maybe there is a path from U to V, but no path from V to U. Right? So just remember this is strongly connected property that every pair will have path in both the direction. So this is one strongly connected graph. Now let me extend this graph so that it does not remain strongly connected. Let's say I add some more nodes and vertices to this graph. So let's say I have this graph, okay? And now we can at least easily see that it's not a strongly connected graph. So can you identify one pair of vertices which are not connected in both the directions? Just a pair of vertices. Yes, A and B is one, right? B and D is no, B and D, right? Yeah, these are correct options. So from A to B, there is a path from A to B, but there is no path from B to A, right? So in fact, B has these outgoing edges, but they will not take us back to A. There is no incoming edge to A, first of all. It's similarly BD is another pair. So the moment I find one pair of vertices, I can safely say that the graph is not strongly connected. So when I know that my graph is not strongly connected, the next interesting problem is to decompose or partition this graph into strongly connected components. So what I mean by that is I need to identify a component which is strongly connected. So for instance, this is strongly connected, but then at the same time, I must also see whether I can extend it further. It must be connected in the maximal sense. So let me explain it in more clearly. So let's say I just pick these three vertices, G, I, and J. Uh, Is this subgraph strongly connected, G, I, and J? This is a strongly connected, right? It's a cycle. I can easily see it's a strongly connected. But I will not call it a strongly connected component because I can extend this further. Okay, so for instance, even if I include these three more vertices, if I take all these six vertices together, they also form a strongly connected subgraph. Okay. Okay, so this is also strong. So as long as I can extend, I can add more vertices to my smaller strongly connected subgraph that I begin with. I'll keep adding the new the vertices as long as it is strongly connected. I'll call it a strongly connected component when I am not able to add any new vertex to that set and still claim that it is strongly connected. So for instance, once I have these 6 vertices, do you think we can add more vertices to this subgraph and still have the property of a strongly connected holding? Is the question clear? Can I add one or more vertices to this strongly connected subgraph and so that the resulting subgraph is also strongly connected? Which vertex can we add? Okay, let me try to add E to this. Okay, so one of you is suggesting E or F, and the other is suggesting B, C, E, and F. Let me try to add vertex E to this subgraph. Do you think this is strongly connected? So this part was strongly connected, right? Now you are suggesting add E to this. Is this also strongly connected? No, right? Similarly, if I add F to this, this is not strongly connected. And these were the vertices which were directly connected to this part. So adding any more vertices will not help at all. We need not even care about these remaining vertices because they are going via E and F. So since adding E or F does not help, we can just ignore the other vertices. So at this point, when I have these just six of these vertices, we have that they form a strongly connected subgraph. And also we cannot extend that subgraph any further without maintaining the strongly connected property. Right? If I try to add one or more vertices, then the subgraph will not be strongly connected. Right? So at that point, when I have a strongly connected subgraph, which I cannot extend any further, that is referred to as a strongly connected component. So by component, I mean must be maximal in that. It must be maximal with respect to the strongly connected property. Is this clear? What is a strongly connected component? Sarvesh? So that is one strongly connected component. Let me mark it. Now I want to identify other strongly connected components in this graph. In fact, I want to partition all the vertices into strongly connected components. So every vertex will fall into exactly one strongly connected component. That is what I want to do. What about the vertex A? If I pick any single vertex in the graph, that is already strongly connected, right? Trivially, it is strongly connected because there is just one vertex. So A in itself is strongly connected, but is it a strongly connected component? Meaning that can I add more vertex to A, more vertices to this subgraph, and still have the strongly connected property? Yes, I cannot extend it any further. The only vertex that I can try to add is B, but then I know that I have a path from A to B there, but there is no path from B to A. Right? So A alone is a strongly connected component. Okay. Similarly, by similar reason, D alone is a strongly connected component. Okay, so far I have identified three strongly connected components in my graph. There are two components which have just one vertex in each, and then there is one component, one large component with 6 vertices. Now I have to deal with the remaining 4 vertices. So again, it should be clear that BE together is a strongly connected subgraph, right? Because there is a path from B to E and also a path from E to B. Okay. So this is a strongly connected subgraph of this graph. Is it a component? Is it a strongly connected component? Can I extend it any further? Can I add either C or F to this subgraph and still maintain this strongly connected property? No. Right. So it means the notion of strongly connected component is clear to both. This is one SCC, okay, and CF is another strongly connected component. Okay. So given this entire graph, I can partition it into 5 strongly connected components, 1, 2, 3, 4, and 5. So here is the interesting problem. Given a directed graph, I want to identify all the strongly connected components. So here it was a small example. You know, we were just trying to look at the graph and identify the strongly connected components in the graph. Sagar, we want to say something or message? Okay. Okay, so so by looking at the graph, we were able to identify the strongly connected components. So let's say in general, am given a graph, directed graph, and I want to identify I want to write an algorithm, come up with an algorithm to identify all the strongly connected components of the graph. So what can we, how do we use DFS to solve this problem? So that will be our next goal. Okay, using DFS, in particular, will again try to use these finishing numbers to identify the strongly connected components in a graph. Okay. So let's make some observations out of this strongly connected component. The first observation is as follows. If I, you know, think of each strongly connected component as a vertex. So let's say I take two strongly connected components in my graph, this one and this one. Okay. Forget about the other remaining part of the graph. Just focus on these two connected components. Can I have edges between two connected components, two SCCs, such that one edge is pointing, both the edges are pointing in different direction? Is that possible? Is it possible to have an edge like this and an edge like pointing in the forward direction? So my question is, let's say I have two strongly connected components. Okay. And I look at all the edges that run from one strongly connected component to another. There can be multiple edges between these two connected components. Okay. So this is component 1, this is component 2. Is it possible to have the edges oriented in different direction? One edge going from C1 to C2, another going from C2 to C1. Okay. So it is not possible, okay, to have the edges in different direction. Why? Because let's say this were the case. Let's say I had just two edges between the components C1 and C2. there is one edge going from C1 to C2 and another edge coming from C2 to C1. What does that mean? Let's say I have a vertex here, some vertex u in this, and another vertex v in this, in the component C2. Then do you see that there is a path from u to v? Yeah, it will become cyclic. So first thing is, because of this edge, we will have a path from u to v. Okay, so you can be anywhere in this, inside this component. We can be anywhere inside this second component. And this was a connected component. So from u, I can go to whatever node connects to v. And via this edge, I'll go to C2. And then there will be a path which will take me to v. So there is a path from u to v. Similarly, because of the edge in the other direction, I'll be able to find a path from V to U as well. Right? And this is true for any pair of vertices UV such that U belongs to C1 and V belongs to C2. That means every pair has a path in either direction. And I should be, in that case, this is, this violates the fact that C1 was a connected component, strongly connected component, because I can extend it by adding one more vertex. In fact, I can extend it by adding all of these vertices, and I'll get a larger strongly connected component. Okay, so we cannot have edges in both the direction between any two components. All the edges will be pointing in the same direction. Otherwise, this will create a cycle, right? Edges in different direction will create a cycle, and I should be able to merge both of these strongly connected subgraph into one single strongly connected component. Okay. Okay, so you can also observe it from here. If I take these two components, both the edges were in the same direction. Similarly, if I take this component and this large one, there is only one edge. Here also I have just one edge. But I think, I hope this makes it clear that between any two components, all the edges will be pointing in the same direction. Okay. So if you view this as a single vertex, every component as a single vertex. So once you have identified all the strongly connected components in the graph, so let's say this is one single vertex, large vertex. In fact, let me draw it separately. So I have like 5 components. So I have, for each component, I'll have a vertex. So this one is vertex. This one corresponds to the vertex A. This one corresponds to D. This one has B and E, so let me label it as BE. This one has C and F. And here I have G, H, I, J, K, and L. Let me just write it as GL, okay, G to L. So this node corresponds to this component in the original graph. Okay. So I'm just compressing every component into a single vertex. Now I want to look at a graph on this component. So there is, in the original graph, I see there is an edge from A to B, right? So I'll just put an edge here from A to BE. Okay. Similarly, from B to D, I had an edge. So I'll put an edge from BE to D. Then between BE and CF, these two components, I had two edges, right? Parallel edges, same direction. So I'll just put one single edge here, BE to CF. Okay. Similarly, from E to G, I had an edge. So I'll add an edge from BE to GL. And C, there was an edge from F to H. So here I'm going to add an edge from CF to GL. So this is the graph of strongly connected components of the original graph. So let's say the original graph was G. This entire graph was G. We identified all the strongly connected components of G. And now I just want to look at the graph of the strongly connected components of G. What can we say about this graph? Can this graph have a cycle? Is it possible to have a cycle in this graph? No, right? Because of this I mean, if there were a cycle, then I should be able to merge them into one single connected component, but that is not the case. These are separate strongly connected components, so I cannot have a cycle here. That means this graph must be a directed acyclic graph. It must be a directed acyclic graph. That is our first observation regarding the strongly connected components. Now, since it is a DAG, it must have source and sink vertices, at least one source vertex and at least one sink vertex. So for instance, over here, A is a source vertex. There are no incoming edges to A. D is a sink vertex. There are no outgoing edges from D. Okay. G to L, this is also a sink vertex. Okay. Now BE, it has incoming edges as well as outgoing edges. So this is not a source or a sink. Similarly, CF is also not a source or a sink. But since this is a DAG, I must be able to identify at least, there will be at least one source vertex and at least one sink vertices. Okay. They can be more than one as well. Now, given this property about the graph of strongly connected component, that it is a DAG and therefore it will have source and sink vertices, let me ask you a simple question. Let's say I have a directed acyclic graph and I perform DFS on that. Okay, it's a simple directed acyclic graph I have, and I do a DFS on that. Then which node will correspond to the largest or the highest finish time, and which node will correspond to the smallest finish time? So I have a DAG. I do DFS on the DAG, and then I want to understand the following questions. First question is node with highest finish time. Can we say something about that node? What kind of node it will be? And second, I want to understand the node with lowest finish time. What kind of node it must be? Is the question clear? I do a DFS on DAG. Okay, I do a DFS on a directed acyclic graph. When I do DFS, every node will get a start and a finish number. Now, what can we say about the node which has the highest finishing number or finish time, and also about the node which has the lowest finish time? The answer to these questions is like it will be either be a source node or a sink node. Highest is sink and lowest is source. Why? why source is lowest? Just think about the, I think, try to answer this question based on the algorithm that we discussed for topological sorting. We order the vertices in decreasing finishing time. Yeah, we start from source. So reaching to sink takes time. Yes. So what will happen is I'll start from a source vertex. Okay, let's say the first vertex is a source vertex. So I started exploring this, and uh, what to say, whatever nodes are reachable from S, okay, all of those nodes we will assign a finish time which is smaller than that of S. Okay? So when I come back to S will get the highest, this source node will get the highest finish time. See, the algorithm that Professor Madhavan had discussed in the course lectures, he uses this other simple algorithm for doing the topological sorting, right? Identify a source vertex. Then that should be the first vertex in the graph. Any source vertex in the graph has to be the first vertex in the ordering. Then remove that node and the edges from associated edges from the graph. I'll be left with another directed acyclic graph. Again, identify a source vertex, and so on and so forth. Okay. So what it means is that the first vertex has to be a source vertex in the graph. Now compare it with the algorithm that we discuss over here. We run DFS and then order the vertices in the decreasing order of finish time. So of course, the first vertex that I have in the ordering has to have the highest finish time, and it must be a source vertex. Okay. Similarly, if you look at the last vertex in the order, since all there won't be any outgoing edges from the last vertex in the order, so it has to be a sink vertex. All the edges are incoming to Vn. Okay, so it must have the smallest finish time. So source will have not just the higher, it will have the highest. So one of the source nodes will have the highest finish time. This is going to be a source node. There can be multiple source nodes, but whichever node has the highest finish time, it has to be a source node. And similarly, node with the lowest finish time must be a sink node. Okay. Now let's we have some 5 minutes, 5 to 6 minutes. Yeah. So let's discuss another property of this strongly connected components. Let's say I have two strongly connected components in a graph. They can be multiple. Just pick two of them. Let's say I have 1 and 2 second strongly connected component. This is C1 and C2. Okay. And so that all the edges going from C1 to C2 are in this direction. Right? So in that case, in my graph of strongly connected components, I'm only going to put one single edge. Right? So there is, say, one single edge from C1 to C2. Now forget about the other components of the graph, other parts of the graph. Just focus on these two strongly connected components. So there are a few vertices in C1, a few in C2. Okay. In C1, I can say that if I pick any two vertices, they are connected in both the direction. In C2, if I pick any two vertices, they are connected in both the direction. There is a path in either direction. Now, here is a question. Just think about it and answer. If I do a DFS just on these vertices, okay, so vertices, of course, there will be edges as well. Then there is an edge from C1 to C2, and I have some more vertices here. If I do a DFS on these vertices, what can I say about the maximum finishing time of any vertex in C1 and the maximum finishing time of any vertex in C2? Like, how do they compare with each other? The question is, if I take these two components C1 and C2, let's say I want to look at the finishing time of every node in C1, U in C1, and I look at all the nodes in C2, okay, V in C2, look at their finishing time, pick the node which has the maximum finishing time. How do these two numbers compare? No. So it's not like C1 is source or C2 is sink. Just that I'm having two components from the graph. For instance, I could have just these two components from the graph. So neither of them are source or sink. Okay. So I'll pick two arbitrary components from the graph, from the strongly connected component graph, such that there is an edge between the two components. Now, the question is, if I run DFS on just these vertices, and now once I'm done with the DFS, every node will have a finishing time. I look at all the nodes in my component C1 and look at the maximum finishing time that I have assigned. I do the same thing for C2. The question is, which one will be larger of the two? C1 will be larger. And why? Okay, so maybe, oh, is it? So how long it has been happening? It was a bad day. Probably my, yeah, videos are something blur. I see that in later when I uh, check the recording, I see that in, yeah, as long as voice is clear, it should be fine. Okay. So the answer is right from both of you. This has to be larger, and here is the simple reason. Yeah, there is an edge from C1 to C2. So if you want to prove it formally, you should prove it like this. So you do a DFS on these vertices, right? So when you do DFS, you have to first pick up the vertex from where you want to start the DFS. So one option is that I pick a vertex from C1 and I start my DFS from here. Now, since I pick a vertex from C1, right? So let's say I pick a vertex from C1. When I do the DFS, I will be getting one single DFS tree. And here is the reason why, because from U, I can go to any vertex in C1, right? All the vertices are reachable from U. So I'll be able to, in this DFS tree, I will have all the nodes of C1. Plus, when I come back to, plus there is an edge from C1 to C2, right? So in this tree, there will be a node from where I can start exploring the vertices of C2 as well. And once I reach any vertex of C2, from there I'll be able to reach all the other vertices of C2. Okay, so if I pick a vertex U from C1, I'm going to get a single DFS tree which will have all the vertices of C1 and C2. And since U is going to be my root node, it will have the largest finishing time, right? And that is coming from C1. The other case is, what if I start DFS from a vertex in C2? So let's say now U belongs to C2. In that case, when I do DFS from U, where U is in C2, I'll only be able to traverse the vertices which lie in C2 because there is no way for me to go to C1. Okay, so I'll have one DFS tree which will have all the vertices from C2. Okay. Now what we do is, because I have to run DFS on the entire graph, I will restart my DFS from one of the vertices in C1. So the situation will be something like this. So C2 is, for C2, I'll get a DFS tree. Okay. So here is a node U in C2. I'll get a DFS tree. And then I will restart another DFS call from a vertex V in C1. V in C1, and we will traverse all the vertices in C1. So here I have all the vertices of C2, here I have all the vertices of C1, and there will be this black edge which connects some vertex in C1 to a vertex in C2. Something like that. Sorry. So the edge is going from C1 to C2, yeah. So this direction. And this has to be a cross edge. Okay, so see, if I started my DFS on a vertex in C1, I'll get a single DFS tree. If I start my DFS on a vertex in C2, I'll get two DFS tree in my forest. Is this clear? Yeah, and now you can easily see that which node will have the highest finish time, U or V? V, right? So because U, I start at time 0, I start exploring U. At time say 10, I'm done with U. Let's say there were just 5 vertices in C2. So I'll assign it a finish time of 10. Then I start exploring V at time 11. Let's say there were some vertices here. I'll assign it a time, whatever finish time to V, but that has to be the largest finish time. Okay, so no matter where you start your DFS from, either a node in C1 or a node in C2, it will always be the case that the maximum finishing time of any vertex in C1 is going to be larger than the maximum finish time of any vertex in C2. Okay. Now, based on these observations, we will in the next session discuss the algorithm. So if you have understood all these parts, designing the algorithm will be easy. This is due to decreasing order of finish. So I do not understand this question. Can we say that this is due to decreasing order of finish time? All we are saying is, if I if I do my DFS starting from a vertex in C2, in that case, it is true that every node here has a smaller finish time compared to any, I mean, you pick any pair of nodes in these two trees, this node will have a smaller finish time than this. That is true. But if you do it starting from C1, then it need not be the case. So all we can say is that this will always be true. Okay. Yeah. So think about this property, this question, and, you can also try to see, the question that you are trying to ask, whether we can say it for every pair or not. give it some thought, should be clear. Okay. So in the next class, we will describe the algorithm in full detail. But if all these properties are clear, then algorithm is not that difficult. So tomorrow we will have a class at 3. Okay. Okay, dear. So I'm once again sorry for the today's session. Tomorrow I'll try to see if my speaker can be fixed, and or I will use some different, maybe my iPad itself to take the session so that there are no issues. You don't have to type everything. Yeah, maybe Sagar, tomorrow I'll try talking to you. If my speaker works, then we can have a discussion. Okay. So I'll end the recording now, and thank you. Thanks to both of you for attending the class and being very interactive as well.